Okay, now that we know how to draw these structures, we want to see what their shapes are going to be like as well. So carbon dioxide, I'm just going to go ahead and put this one on here. We've drawn it enough times, and it fits normal Lewis rules. We're going to see kind of why we make that triangular shape, those three regions on the oxygen. All of this is there, and we look here and we get a 180-degree angle here between the carbon and those two bonds around the carbon, and that's going to give us a shape out of that. Okay, we never really label that, but we just want to look at it. This is going to be a linear geometry. Now there's two actual names. The geometry, the molecule geometry, molecular geometry is linear. The total number of regions is still 2. There's one region here, there's a second one there. There are 2 regions. The electron pair arrangement is still linear as well, or the orbital geometry. When we do SO4 2-, let's go ahead and go through those calculations. We've got 6 times 4, 24 electrons here, 30 with the sulfur, and 32. So we've got 32 electrons on this molecule. 5 times 8 will give me 40. There's 5 atoms. So we need 8 over 2. We need 4 bonds, which is doable with 4 oxygens. So let's put the sulfur in the middle. 4 oxygens on the outside. And this is where it just helps to count by 8s. We know that all of those oxygens are going to have full octets on the outside. Everything on the outside will. And that takes care of all my 32 electrons. So I've got 8 here, 16, 24, and 32. So just an easy comparison to that 32 that we started with. If you know going in that you've met that 32 need, you know that your structure is more or less done. Or if you haven't met it, you know how many are left over. So this structure here has 4 different regions on it. They're all bonded, so that means the electron pair arrangement and the geometry are going to be the exact same. There's 4 different regions. That's tetrahedral. All right, 4 regions around the sulfur, and there's our structure. To get to BRF3, we're going to look there. There are 28 electrons, 4 times 7, and 4 times 8 gives me 32 to have full octets. For a difference of 4 over 2 gives me 2 bonds. Now that doesn't work with 3 atoms, so we don't want any of that. We just want the 28 electrons. And here's where the counting by 8s really helps us plan our structure. Bromine's in the middle. The fluorines will be on the outside. Okay. Now, if we know that those fluorines are going to be on the outside, how do I arrange them? Because we can get a little foresight here and spread them out. The 3 fluorines will have 8 electrons each, full octets. So 8, 16, 24. That means I'm going to have, in order to get to that 28 number, I need 2 lone pairs in the middle. So we're going to spread them out. That means I've got 5 regions of space. I've got these 3 here, and let's show that. Here's my 8 on the fluorine, 16, 24. I need 2 extra lone pairs. That tells me I've got 5 regions here, and it lets me put those off at the angle, and then that gives me my molecular geometry. Is T-shaped, and the orbital geometry, or the electron pair arrangement, has 5 regions. That's going to be trigonal bipyramidal. Okay, and I'm using abbreviations just for ease of writing here. All right, let's get to the next ones here. Same list, just a new slide. XeO4. Oxygen has 24 electrons in it. There's 4 of those. And then the xenon, that gives me 32 electrons here. 5 times 8 gives me 40 to fill the octets. So 8 over 2, 4 bonds. 4 bonds is good. Xenon's in the middle. And all the oxygens will be on the outside. So 8, 16, 24, 32. That's how many we have in our structure. So 32 is going to be a good number. There's no extra electrons on the xenon. We just fill our octets. The electron pair arrangement and the geometry both have 4 regions. 1, 2, 3, 4. And those are tetrahedral. Last one, we'll get ICl2. With a positive charge. If we did a negative charge, it would actually change the shape. There are 21 electrons there, plus the 1 charge. The plus 1 gives me 20 electrons. And 8 times 3 gives me 24 electrons to fill the octets for a difference of 4 over 2. 2 bonds. And 2 bonds will work. So iodine goes in the middle. And again, let's plan ahead. There's going to be 2 chlorines on the outside to give me 16 electrons. And we need 20. That gives me 4 more. So that's just going to be 2 lone pairs at the end. Now we could draw the chlorines like this and then say, oh, I've got those 2 extra lone pairs on there. But deceptively, that looks linear, and we know that 4 regions does not have any linear structures with multiple bonds. So if we plan ahead right, we can put our extra chlorine this way. If we know that we're going to have these 16 electrons, and I only need 2 more lone pairs, I've got this full octet on the iodine, which is standard. It's a tetrahedral electron pair arrangement, but a bent geometry. So we still have 1, 2, 3, 4 regions on the iodine, so that gives me tetrahedral, but only 2 of them are bonds, so bent. Okay, and we would need to be able to apply this. Every molecule has 2 names to it: the orbital or electron pair shape, and the molecule shape, which just considers the bonds.